This lecture is about understanding some of the basic ideas or basic and most important ideas of quantum mechanics. Not all, but some of it, some of the most crucial ideas to which we need at least in the in maximum of this course. And these basic ideas are namely superposition principle, from which the concept of probability, amplitude and wave function will come, and we will understand that how we are giving away determinism, which is something what we what is there in classical mechanics, and we intuitively think the world must be deterministic, and how that goes away in this formalism of quantum mechanics. Then we will talk about uncertainty principle and try to understand the concept of measurement and how it is a very crucial thing in quantum mechanics. And in superposition principle, of course, naturally we will discover there that that the most natural way to talk about this non-deterministic physics is through an object called wave function or probability amplitude, rather not the probability, which is not a measurable object, but its effects are very clear. All these ideas will be presented through two of the most landmark experiments in the which played a major role in the development of quantum mechanics, and those landmark experiments are double slit experiment and Stern-Gerlach experiment. Both of these experiments basically tells you the same thing, but in a different, slightly different way, and we will go through that in details. Followed by that, we will talk about measurement, the idea of measurement, again using these two experiments, and finally we will spend some time on cat experiment and all, like the hypothetical cat experiment of Schrodinger, and try to understand or try to develop a feel for how all the peculiar phenomena which are happening in these two experiments of Stern-Gerlach and double slit experiment can be understood a little better, and we must clearly set the line between the part of the quantum mechanics which we understand, or at least which we are comfortable with, and the part of the quantum mechanics which is which does not make any sense, but it is still true. So, this is basically this will constitute the conceptual foundation for almost all the material that we will discuss in this course, and these are like they are uniquely quantum phenomena, and then we will try to develop intuitively a language for describing this kind of quantum mechanical phenomena. Now, this language is not like a very alienated language, but we will develop it intuitively, like try to think that how to mathematically represent these ideas, or in terms of a and develop a formalism in which we can do calculations and connect these abstract ideas to real world measurable quantities. And finally, there is a fifth topic which I am not going to cover now, which is the one of the most unique phenomena of quantum mechanics, and it plays a very major role in many of the quantum phenomena and many of the modern research, but we will we'll talk about it at the very end stage of this course, which is the non-locality or notion of entanglement. So, right now we will focus on these basic ideas which you are already familiar in some form, but we will revisit these ideas and try to understand a bit deeper and try to probe that up to what extent it makes sense, and where it stops make sense, and which part you can access and which part you cannot access, and then try to develop intuitively a mathematical formalism. A little later in the course, we will do the mathematical formalism in a much more like mathematicsy way, not like a physicsy way where we develop the thing intuitively. Okay. So, with this basic outline, let me go into the double slit experiment, which we already discussed in a and I realize that most of you know quite well about double slit experiment. So, we will quickly go over this. So, what is the double slit experiment? The double slit experiment is simply a setup where you have a source of something, and then you have a wall which has two holes, and then you have a screen where the source throws away some particle or emits some particle, they passes through these two walls, and then they interact with the screen or deposit with at the screen. So, let us do something very classical and intuitive. Let us start with a gun which is firing bullets, some let us say some very advanced machine gun which can fire capable of firing bullet at a very fast rate, and then it passes through two holes in the wall, and then let us say this backstop is a is a metal sheet where it hits and creates a dent. So, if you do this experiment where you keep shooting this bullet through this towards this wall, and then you collect and then you count the number of dents on this metal sheet, then you know where these metal sheets where this bullet hit struck the metal sheet, and then you plot to the probability, or you can say the number of strikes at a particular point of this metal sheet against the coordinate or the this one dimensional x axis, dividing it by total number of shots fired. That gives you the probability basically. So, what happens in this experiment? If you let us say you make it simplify the experiment by closing one of these two holes, you close the hole number 2, you only have hole number 1. So, if you shoot bullet towards this wall, it can only pass through hole number 1, because that is the only way to go on the other side of that wall, and then you will expect that there will be a deposition of, or the number of dents here is higher in this region, and that will give you this P1 plot. Similarly, you do the same, play the same game with by opening the hole number 2 and closing the hole number 1, and you will get a similar plot which is the P2. Now, if you open both of these two, you would expect that the most number of that the probability of finding a dent on the wall will be basically a simple superposition or addition of these two probabilities, and that is basically you will get this plot, which is P12 is P1 plus P2. That is totally intuitive, and something you can it's obvious, there is nothing weird about it, and you know obviously that is how things work. Now, let us play the same game with a wave. So, the setup is again the same. We have a wall and we have some detector, and let us say the setup is following. I have a wave source which is basically a motor in a, so this is a vertical shot of the wave source, which is a motor which vibrates in and out of the plane of the screen, and it generates water wave. So, there is water everywhere and generates water wave, and then you have these two holes through which the water wave passes, and these waveforms meet at the screen, and the screen let us say have some intensity detector. You can think it as some, okay, how can I think of an intensity detector of water wave? Let us say you have some marker here where the depending on how high the water wave, the wave form is, this wall gets wet till that height, and then you know the wave was higher there or lower there, like the amplitude was higher or lower. Now, if we plot the intensity of the wave again by playing the same game, by closing this second hole, what you will get here is basically this plot I1, and again similarly by closing the first hole you will get an I2 like this plot, which is totally makes sense. But the thing you know that what happens for waves, waves are not just amplitudes, they are amplitude and a phase, and this phase can interfere constructively or destructively, and that will cause a pattern, an interference pattern, when you have a when you open both hole and hole 1 and hole 2, and that is well understood in terms of this interference phenomena is well understood in the context of optics. You have studied Young's double slit experiment, and what how you explain this phenomena by saying that these two waves, these two wave fronts coming from the hole 1 and hole 2 are described by H1 and H2, which is basically an amplitude and a phase, I omega t and I omega t, and then you have a intensity of this wave front is given by the square of this H, which is where the complex parts cancel, and the total intensity is basically, when you get the total intensity, you sum these two waves, which is you sum them as a whole, which is basically this object, and then you take the square mod square. So, this becomes basically H1 plus H2 square becomes H1 square plus H2 square plus 2 H1 H2 cos delta, which is the phase difference between them because of the difference of the path traversed, and then you finally get the expression of the intensity, which is I1 plus I2 plus 2 I1 I2 cos delta, and this cos delta part causes your interference pattern. This is something you know very well, and you have studied it in great details in optics, but it is true for any waveform, and it was in fact the first experiment performed to establish the wave character of light, the Young's double slit experiment, which was performed in very early 18th century. Okay. Now, we know these two phenomena, and it makes sense in our intuition very well. It didn't make very clear sense to, because people believed light is a particle when before Young's double slit. I mean at Newton's time, for example, Newton had that theory that light is a particle, but it took a while for people to figure out this, and the reason is simply for light is that for light the kind of dimensions you need is not so easy to achieve, but it is well, it is not easy to achieve, it is not entirely a right statement, but easy to observe and notice. For example, if you just make a bring your fingers very close to your eyes and try to look at a light source, you can see this interference pattern between your fingers. This is a very simple experiment one can do to immediately see that the light interference effect, but of course to recognize that pattern as a proper and formulate this whole thing, that took a long time. Okay. Now, let us play the same game using an electron gun. So, here the experiment is following. Again, instead of a bullet you have an electron gun, and the electron gun is nothing but you have you are heating some metal, let us say, which have a single electron in the outer shell, and passing the metal through some collimated beams, like through some channels such that it is collimated and not spreading around everywhere, and then they are forced to fall on a wall, and these walls again have two holes, and then the electrons are passing through them and coming to the other side of the wall and reaching at a backstop, which is a film of some kind of a film where these electrons are getting deposited, and when they are getting deposited they create some mark there. Let us say you have this black screen, and then the electron hit there, it creates a white dot. Okay. So, this is the experiment. So, again you play the same game. You know that the electrons are like a lump of energy, which is like the most intuitive way to think about it is as a particle in the classical sense. So, you will see if you close the hole 2, you will see that intensity distribution or probability distribution as P1. Similarly, if you close the hole 1, you will get this P2, but then the surprise happens, which is something that was seen from an experiment, was that when you open both hole 1 and hole 2, you get an interference pattern, which is something you do not expect for a particle like electron. So, what does it mean by this interference pattern? So, by that I mean, let us say you are So, let us try to understand how it is happening. You might wonder that the electrons are probably doing some kind of although it does not make a lot of sense, that probably doing some interaction with each other, because a large number of electrons are thrown towards it, and they are one guy is disturbing or knocking off some other guy, or some funny thing is happening. So, let us say we do the experiment in a way that we throw these electrons at a very low intensity, which means we throw like 1 electron every day, or like one electron every hour, that is like too slow, such that when you shoot 1 electron, somehow it is so you have a ability to, let us say, control this. You have, it is basically just a very low intensity beam. This 1 electron will come through it and deposit here without talking to any other electrons from the source. So, you will expect that this electron will come here, either go through hole 1 and deposit here, or go through hole 2 or deposit here, or somewhere like that. So, this is what you expect. One of these two events will happen, both cannot happen at the same time, and then the second electron will come and do the same thing. So, here is a snapshot of the screen, what will happen at the screen over a very long period of time. So, let us say after every few hours you are checking this screen, and you first saw okay, some dots, some electrons have arrived in sub panel A. Then after some time you saw again, okay, some more electron have arrived. After some time you saw some more electron and more electron and more electron. Gradually you will see, if you wait for a very long time, you will see again an interference pattern, which is completely different from the bullet experiment and something you did not expect. How to make sense of that? So, that means even for 1 electron, somehow there is a wave associated with that, because there is no way these 2 electrons are interacting with each other and causing some interference effect. It is even a single electron itself has a wave associated with that. What does it mean? That it is creating some kind of interference. Even a single electron is creating some kind of interference. How can it happen? So, one way you may think, oh, the electron is coming here and splitting into 2 halves and going through both of the holes at the same time, and they are interfering and coming here. Or the electron is coming here and then taking some, going there and then taking a circular path and doing some funny business, and then reaching here somehow with some kind of a waveform. So, it is not, there is no way to make sense of that. How can it happen? So, let us say you do another experiment to see exactly the electron is passing through hole 1 or hole 2, because your classical intuition says it can be passing through one of the holes at a time, and if it passes through hole 1, it cannot pass through hole 2, and there is no question of any kind of interference. So, to see that, let us say you put up a light source at this place and you observe it. So, let us say you are observing at placed an observer at some detector at hole 1 and some detector at hole 2, and what is the job of this light source is that if the electron is passing through hole 2, the light source will send a photon from the light source will basically scattered from the electron, and then it will come to the observer, and that is basically how you see things. A photon or a light particle scatters from an object, and then the scattered photon enters in our eye and we see that object. So, that is basically that experiment. So, if the detector here or the observer here sees that the electron is passed through here, then they report that okay, the electron have passed through 2. So, let me call that probability P2 prime, and the prime is because this is a different setup from the previous setup, because now you have a light source and another observer here. Similarly, the observer, if the observer sees passed through hole 1, then they will report that okay, it passed through hole 1, and that will be plotted as P1 prime. Now, when you do that experiment and the observer reports that okay, I have seen this to be passed through 1 or 2, you again get the outcome you get is like the bullet experiment, which means as soon as you observe or try to see it, the interference pattern is gone. So you might be thinking that maybe I am disturbing the experiment in this process of observing, which is probably true, because the act of observation is basically disturbing the electron by so you are throwing a photon, and that photon is probably forcing something on it, and then it is behaving in a particular way. So to see that, let us say you decide to disturb the system very little, like not as little as possible. So you dim your light source. You dim your light source, that means you reduce the momentum of your photon, and you keep dimming, and if you even then you will see that okay, it is still behaving like bullets, like this kind of plot. Now if you keep dimming, there will be a point where you won't be able to see anything, that you won't be able to tell that whether it came passed through 1 or passed through 2. As soon as you reach at a stage where you cannot tell that whether it passed through 1 or passed through 2, you will again get back this interference pattern. So it is a very frustrating situation. It is like maybe sometimes I do not know, maybe it is not the best analogy, but you can think of when we were kid, we sometimes tried to watch when does the light inside the fridge closes down, shuts off, it becomes dark. So in a good fridge you will see that when you try to close the door and it comes very close to closing, the light is on, and then at the point you close the door, then the light is off, but you cannot say, because the door is closed, you have not seen inside the fridge. Of course it is not true for all the fridges. Some fridges have a longer switch, because the light inside the fridge works like a lever which you press, and when the door closes it is fully pressed and the circuit disconnects and light is off. And other way it is when you open, as soon as you open it is on. But usually it is you can in principle always make the circuit such that it is not the case. But here it is different. Here it is, no matter what you do, if you know that where from which hole the electron have passed, you immediately get a bullet like behavior. But when you do not know whether the electron have passed, you get a interference pattern. So it first the thing to notice that whatever happens here is observation dependent, or the state of observer dependent. So your knowledge about the system tells you, so your knowledge about the system tells you what the influences the outcome of the experiment. And secondly, there is an up to an extent where you can say things. So these are the main puzzling outcomes of this experiment. So now let us try to formulate this, what we have just seen so far. Let us try to formulate and try to see if we have set up a theory at least for that, purely phenomenological. What we have seen, we will try to describe it, but in a scientific language. But and then we will try to see if we can answer why it is that way, or how come it is that way. It is peculiar, but let us just try to get a phenomenological language. So drawing from the analogy of electromagnetic waves or any other waves, it makes sense that the probability of an event is given by the square of absolute value of a complex number phi, which we call the probability amplitude. Just like here we needed an amplitude and a phase, a complex number, in order to describe something, describe an wave, and the actual intensity of the wave is square of that. So here we are seeing a wave like phenomena, so we have to have a wave like description. So that way we have a similarly the probability cannot be complex, of course it is a, but the probability is acting like as if it is made of a complex object which has a amplitude and phase, and the phase can cause a interference. So the best bet is to describe the probability as square of that complex object, which you call as probability amplitude. And the second observation is, when an event occurs in several alternative ways, the probability amplitude of that event is the sum of the probability amplitude of each of the ways considered separately. So phi is so when an event occurs in two different ways here, like either it goes to path 1 or path 2. So the probability of the of this event is basically sum of the probability amplitude of the way to describe this event is in the language of probability amplitude, just like the wave case, where you write down the wave add the probability amplitudes, and the probability of the event that when it have passed either passed through 1 or passed through 2 is basically square of the sum of these probability amplitudes, which is again different from the bullet case. In the bullet case you add the probabilities, here you are adding the probability amplitudes. Again it is just an analogy from the wave. Now the third point is, if an experiment is performed which is capable of determining whether one or other alternative is actually taken, the probability of that event is the sum of the probability of each alternative. This is again the fourth experiment, where you somehow know that which of the alternatives is chosen. As soon as you know that, then the probability of that event is the sum of the probability of each of these alternatives. So this is basically the okay. So what we just discussed is that the way some way to describe this all these experiments with bullets and electrons, and we found that that the only sensible way to so let me summarize this whole description. The only sensible way to describe this experiment with electrons is by saying that with each electron, individual electron, there is an associated probability wave. Now this might sound like a vague statement under which several things are hidden. So what does it mean? I will come to that. So before that, let me tell you that, so the only way to understand this experiment is by saying that with each electron there is an associated probability wave, and that probability wave is best described just like any other wave in terms of a amplitude and a phase, and that object we call probability amplitude, whose square is the probability. Just like in the case of wave, the intensity comes as square of the amplitude. And when an event occurs in several alternative ways, in this case that means the wave can pass through various the wave can take various paths to reach at a certain point, and at that point a measurement is made to know that where the particle is located. So then when such a thing happens, then you, in order to find the probability of that event, you must add the probability amplitudes, not the probabilities, just like you do for a regular wave. And finally, if you somehow know that out of these several possible ways the event can happen, one of the ways have been chosen already by some means, then the wave is no longer you describe the wave language, then you call it describe it like a regular particle, and you add the probabilities, not the probability amplitudes. So this description has several uncomfortable components. First of all, we are giving up determinism, which means we are now talking already in a language of probability. We are not talking anymore by saying, oh, if I do this, the particle will take this path. Now we are trying to say, oh, even for a one single particle, it can either go through path 1 or go through path 2, if that is the classical way of thinking. If that happens, then of course you add probabilities. But here we are saying that the particle can go through both path 1 and path 2 at the same time. That is the meaning of saying there is a wave associated with it. This is very mind boggling and very confusing, and our classical brain can make no sense of that. So then this particle is kind of interfering with itself, it is like that. So even for a single particle there is a wave associated, and then that means that and if there is a finite probability of that, then it have either it can go through both. But it is only true if you are not looking at the particle. If you are looking at the particle, then it is a particle again, then you know which path it went through, and then all this structure goes away. How is that true? can one explain this one level deeper, like what this is of course what that's the only way to make sense of the experiment, existing experiment, but can one go one level deeper and say, oh, this is how it is happening and that is why it is like that? The answer is no, one cannot. One can certainly construct theories that what might be happening one level deeper, but there is no falsifiable way of choosing between those theories that what is exactly happening. So, that is actually the domain of interpretation of quantum mechanics, and this is more a philosophy department topic than a science department topic at this stage. Of course, at this stage the line between science and philosophy blurs, but it is more a it is not, there is no way to say that what is happening one level deeper of this experiment. So, you can make all kind of speculation, is the electron splitting into two parts, or is it behaving like it is becoming a wave or something else, but there is no way to say for sure that what is exactly happening. So, that is that, and we will try to come in peace with several by several different ways to this. And so, there is no way to go one level deeper to this, and that is basically the best we have at this point, even now, still till the birth of quantum mechanics till date, that is the best we can say. So, what is happening? Let us say that, let us go over it once more. So, everywhere people usually go over this confusing part very fast because there is not much to say, but let us try to slow down here and try to go over it again. So, what is happening here, that the electron comes out of here. As soon as the electron becomes an like comes into existence from somewhere or whatever, the electron is always there with a probability wave, as a probability wave associated to it, but it behaves like a wave till the point when it is not seen. As I mentioned that it could be like as soon as you look at it, it is no longer a wave. But how do I know that it is true? Is because it is giving an interference like Fa. So, what happens, the electron is coming out of a gun like a wave, then it passes through this a single electron, then it passes through either hole 1 or hole 2 or both at the same time, which can happen because it is now a wave, it is not a local object and a lump of matter, and then it reaches here. There is no way to visualize this, and if you try to visualize it, it makes no sense, but that's the only way to interpret the experiment. So, that is that. Now, if you try to observe, so when the electron reaches the detector, that is an act of observation, then it behaves, then it becomes like a particle, and then you get a dot on your screen, then it is no longer a wave, of course, like that is how. So, the act of observation brings it back again into particle nature, but and that is true again if you try to observe it in the middle. So, if you try to observe it at near hole 1 or hole 2, then it again acts like a particle, and then it behaves, then you know exactly its path, and then there is no confusion that whether it went to 1 or 2 or both at the same time, and then it is again particle like. So, the act of observation, this is called in the language of quantum mechanics, or in the jargon it is called collapses the wave function, and it is like performing an measurement, and that will bring it from wave nature to particle nature. But when you do not do any observation, then it is like an wave, but again by wave one means it is a probability wave. So, let it sink in your head for some time, and the only way to proceed is by getting used to it, because there is no way to explain it, there is no way to go one level deeper to it. As I said, later we will go through various other experiment, various other thought experiment for the process of getting used to it, but not explaining it, because there is no way to explain it as of now. There are, of course, there are theories which I'll describe you later. For example, the multiverse theory, the Copenhagen interpretation, the Bohm's pilot wave explanation. Some of it I will discuss later, but those theories are not falsifiable, which means you cannot perform an experiment to say this is happening and that is not happening. So, all of them are probable explanation for what is happening, and there is no scientific way to establish that. So, that is that. Okay. So, now let us proceed further, and now let us try to understand go over the uncertainty principle, which plays an important role in this game. So, let us, you already know the uncertainty relation, so I will not talk about it again. It basically tells you cannot know the position and the momentum of the particle both exactly at the same time, and there is an uncertainty of them, which is, and the bound of uncertainty is given by del x del p greater than h bar by 2, where h bar is the Planck constant, a very small number. So, what happens when you try to look at this same experiment slightly differently? So, let us say again you have a source of electron, and then this electron either passes through hole 1, hole 2, or do some wave thing. So, whatever all the experiment we have seen before, but now we are trying to know that which hole it passed through without directly looking at it, which means without directly disturbing the thing. So, can we do such a thing? So, uncertainty principle actually tells you cannot. So, what does it mean? So, let us say you have these slits, these walls, the central piece of this wall is fixed, but these other two pieces of the wall are connected to some ball bearing or rollers, which means and some very hypersensitive, of course, some nanoscale hypersensitivity, which means when an electron hits the wall moves, and because so if the electron hits the first wall, it will move upwards. If the electron hits the second wall, it will move downwards. If the electron hits the second wall, of course, it does not move. So, there is an exchange of momentum happens here, and that moves the wall. So, that is basically the phenomena. So, what you might think, and let us say you have placed a detector right at the center. So, then you know that when an electron, so you are not moving the detector, or maybe you are just observing at the center what is happening at the center. So, here what might happen here? So, if the electron have passed through the wall number 1, hole number 1, then you will notice that this wall moved upwards a little bit, and then it gets detected in your detector or screen. So, then without directly looking at the which path the electron took, you know that which hole it passed through. And the same way, when it passes through the hole number 2, then this wall moves a little bit downwards, and then you know it have passed through hole number 2 without directly looking at it. So, you might hope that this routine might help you to know that which hole this electron have passed through without actually directly looking at it, and that might solve your problem. So, it turns out when you try to do that, the interference pattern actually goes away. So, why is that? So, remember what happens when you would perform this experiment. So, if you know the momentum of the electron or the momentum of the wall in this setup, again, like think of this whole setup as your system. So, that means if you know the momentum of the wall before the electron hits it, which is 0, and then after the electron hits it, the wall moves. So, you know the momentum change, which is by delta px, and so on. You know the same for hole number 2. But the point happens that when you know the momentum of the wall, you no longer know the position of the wall. That is basically the statement of uncertainty principle. So, what does it mean? It means no longer the holes are located where it is supposed to be located. So, the holes have changed. So, the whole experiment setup have changed, the holes have shifted. So, here is the statement so then what is the consequence of that? So, the consequence of that is that if you perform this experiment with many electrons, so the first electron come here, second electron comes here. So, the first electron, the center of your interference pattern is located at the origin, let us say, but for the second electron, the center of your interference pattern is located somewhere here, somewhere else, and for the third electron, the interference pattern center is located somewhere else. So, that way, so you are, when you are depositing 1000 electrons or maybe many more electrons, you are basically having separate experiments for which the holes are located at different location, which you do not know, because you knew the the momentum, and here is the resolution, which the uncertainty principle gives you the resolution to what you know that. And then because of the shifted interference patterns, the fringe effect or the pattern will be destroyed. So, they will be smeared, they will mixed with each other. So, the uncertainty principle basically protects the quantum mechanics, the peculiarity of the quantum mechanics, which means you take, by any means, if you know the position of the particle accurately enough, like which hole it have passed through, then you lose the interference pattern again. So, that makes sense. So, that is basically what the uncertainty principle tell you. So, there is no way you can know the position of the particle. If you know the position of the particle, then the interference pattern is destroyed. If you try to know it in an indirect way by measuring momentum, then you lose the information about the position to so much that the interference effect of different particles smears with each other, the center of the interference shifts, and then you again get a particle like behavior. So, that is basically it. Now, there are some points which we raised during the class, that so basically this whole picture was to present the wave as the particles as waves, the thinking of waves and particles that came through some different sets of experiments, photoelectric effect and Davison-Germer and all that. So, basically you can again think about the same experiment with light, where photon is like a particle, and then there is a probability wave associated with the photon, and then you get the same thing. So, basically it tells you that any object you can either think it as a wave or think it as a particle and there is no distinction between these two, it is a kind of unification, and that unification actually, so you might observe that any kind of unification tells you that two different objects can be measured in same unit, and that leads to some kind of a constant or a unit. So, here it tells you these two conjugate variables can be are related. So, they are basically called conjugate variables, and one can set up a same unit to measure them and talk about them under the same in the same footing, like energy, time, position, momentum, and all these things which come. So, now this is something very true for any unification. Any kind of unification basically gives you an some kind of link, a bridge between two completely different objects, and sets up a same unit to measure that. And similarly, now let's so here let's think about let's get a sense of the dimension and size of the setup when you do this experiment with other objects like photons or bullets. So, let me remind you that how you get the interference condition from Young's double slit experiment. So, here is a source of light which falls on some wave source, which falls on these two slits, and then it meets here, and d is the distance between the two slits. So, if that d is that distance and theta is this angle, we know the length difference between these two paths, that is given by 2d sin theta, which is this distance, and when that is equal to a whole number of waves, then you get a constructive interference pattern. If it is equal to like m plus half lambda, then you get a destructive interference pattern. That is something you have studied to depth in Young double slit experiment. But that gives you an important idea about the dimension of this setup in order to see and see a interference pattern. For example, if you perform the experiment with Young's double slit experiment with radio wave, which is a longer wavelength, you need this d and everything to be much bigger, or let us say with some other, like let us say, that is why you need such very long arms, and for example, to do an interference effect experiment with gravity wave has like a very big lambda, and then you need a different kind of setup there. You need very like kilometer length interference setup, and so on. And if you do it with gamma ray, you need a shorter small dimension setup. So let us see what is that for photon. So for photon, if you plug into this number, so the wave associated with this the probability wave associated with this, which a particle, is called a de Broglie wave, which has a wavelength that is calculated by h by p. And if you plug in the numbers here, you will get that the photons have a wavelength of 10 to the power minus 9 meter, or the order of a nanometer. And that kind of gap you can create, even as I said, with your fingers. You can look at a light source and bring your fingers very close and to your eyes by making like a pinching structure, but not touching the fingers very closely. Make a very small slit with your fingers and look at the light source and rotate it a little bit, you will see an interference pattern. So you can create an experiment of interference with your hand. But to see it properly in a clear manner, people did this experiment. The Young's double slit experiment was done in early 18th century, and the experiment with electrons was done in around 19th century, like 1925, 1920, around that time. So it took 100 years or more to reach there, because of this resolution, or because of this wavelength associated with electron is 10 to the power minus 11, like it is 100 times smaller. So reach that 100 times smaller scale, it took 100 years. And similarly for bullets, this experiment is if you want to calculate the same quantity, it is order of Planck length, which is an impossibly difficult or almost impossible length to reach. So you can never see this for in any realistic setup interference effect for bullets. But it is true that all of them in principle show that this kind of should show this kind of effect, because there is no reason that any particle should not have this kind of structure. So it is not a theory for small objects, it is a theory for every particle. And similarly for every wave, which you can think again that as a particle, like a photon, electromagnetic wave can be thought as a photon, and then that particle will again have a probability wave associated to it. So this is basically the idea. Okay, now let us talk about some formalism and develop a little bit of formalism with in a very intuitive manner. So we discussed that if there are two different ways of an event can happen, then instead in a classical probability theory you add their probabilities, but here you are going to add the amplitudes. So the law of combining amplitudes can be expressed in a little mathematical language, which you will learn later in linear algebra form, but now let us try to understand it intuitively. So this is an important thing as a physicist you must do. You must have a intuitive feel for the mathematics and treat the mathematics as a language. Do not get lost too much in the formalism, definition and jargon of mathematics. Well, that is a valid way of doing science, but valid way of doing physics, but physicists are not known to do that. The thing about physicists is that the physicists see everything in a very intuitive manner. Not all physicists, but at least I do, and many people do, and like to think pictorially. And the pictorial thing of course does not make sense in this case entirely, but you are still trying to do the best you can, the best picture you can vision, and trying to complement it with the mathematics. So the physicist way of thinking about mathematics is is a bit different from the mathematician's way of thinking of mathematics, and that you will see throughout the quantum mechanics examples. For example, there are many things in quantum in the context of quantum mechanics physicists did which broke all the rules of mathematics. For example, Feynman path integral, people are still trying to make sense of how that works in a mathematical way. It is a whole way to integrate stuff which cannot be integrated in a, or cannot be even defined in mathematics, but it works, somehow it works. So, it is like a it is a complicated separate philosophical debate where I argue that whether mathematics reveal a deeper truth about the nature which is already existing, or it is just a language which human use to describe nature, and that is why they keep finding things which appears that it is already there in mathematics. So, we will not enter in that debate, of course, that could be a very interesting topic to talk about on its own, but for now we will treat mathematics as a effective language. So, here and try to we will learn the linear algebra and everything we need for this course in this course like that. You might learn it more formally when you take a math course, but that will help overall. So, here we want to develop a language, a mathematical language for this. So, let us call this thing the event or the measure act of observation, which you know for sure that a particle arrives at x, which the particle arrives at x is given by this, and the particle leaves at s is given by this. So, in shorthand I write it x s. This is the amplitude of this phenomena. Now, these have two possible ways of this can happen, and the possible ways are it either pass through 1 or it pass through 2. So, if it pass through 1, I will call it the particle left x, reached 1, then it left 1 and reached s, but in between it did not perform a measurement. When you do not perform a measurement, we know that our rule is to add the amplitudes. So, the particle can similarly pass through to reach 2 and then leave 2 and reach at x, which is expressed by this. And since you did not know which way it went and you did not try to perform a measurement, or even if you did, you was not able to extract the information for some reason. So, when both holes are open, you will add the amplitude, which is like this. But if you and you can similarly extend this. So, if you perform a measurement, of course, then you cannot write this, then you have to write P 1 2 is equal to P 1 plus P 2, so you no longer add the amplitude. But now, let us look at a more complicated scenario, which is again expressed can be expressed like that. So, let us say you put another slit in between which has 3 holes called ABC, and first one has 2 holes called 1 and 2. So, the event here is the particle leaves S, passes through 1, then passes through let us say A, and then reach X. So, it could be X to A. So, S to 1. So, the rule is to write it, the rule can be completely arbitrary, but let us stick with this rule and follow some consistency. So, the rule is to start from the origin and from the right hand side and reach at the destination in left hand side. So, S to 1, 1 to A to S, and then similarly for B you will add S to 1, 1 to B, B to X, and similarly all the possibilities. So, all the possibilities will include many terms, and that can be compressed like that. So, it goes to S to slit I, which is I is either 1 or 2, then I to it can go to alpha, alpha is A, B or C, and then alpha it can reach to X. So, that is the law of combining amplitudes, and that you do if you do not know anything about the path of the electron in between. If you know it, then you have to do it went to this and then it went to this and then it came here and add the probabilities. So, that is the rule. Okay. So, now let us revisit the act of measurement within this rule, within this framework. So, the act of measurement is basically now knowing that which way it went, either whether it went through hole 1 or went through hole 2. So, let us say these are the two events, which is it went to S to 1, 1 to X, which we have just discussed, but when there is no act of measurement, when there is no light. So, here you shine a light source here, the electron passes through here, it scatters a photon and it is detected in detector 1, or it scatters a what are all the possibilities that can happen that I am describing here. Electron comes here, scatters a photon from this source and detected in D1. Electron comes here, scatters a photon from the source and detected in D2. Similarly, electron comes here, scatters a photon from this source and detected in D2. electron comes here, scatters a photon from the source and detected in D1. These are the 4 possibilities. So, turning on light is an act of measuring or making an observation, and then we want to ask that what is the probability that an electron starting at source S detected at X while it is seen passing through hole 1 by the detector D1 by scattering a photon from the light source L. So, this is represented by S21, then this act of scattering or measure or observing the electron, which is another probability amplitude A, and then it is going from 1 to X. Okay. So, this together I can write it as A phi 1. Similarly, the electron can pass through 1, scatters a light, can be detected in it can pass through hole 2, it scatter a light and detected in D1, and that will be anything the whatever is seen in D1. We are just talking about all the things which the D1 can see. So, D1 can either see it passing through 1, which is this, or D1 can see it is passing through 2, which is this. So, this is B phi 2, again S to 2, then B and 2 to X. Now, combining these two, if you want to cover that event, that the electron is at X and there was a photon at D1. So, the source is the electron left from S, then it was there was a photon from L, and these are the two emissions, and a detector 1 detected an event, and similarly the detector and the screen found the electron at X. So, this whole process can happen in only these two ways, which is A phi 1 plus B phi 2, and similarly the whole process where the electron leaves from S and reach photon from L, and then the electron reaches at X while there is a photon at D2 can happen similarly in these two ways, A phi 2 plus B phi 1. So, A is the probability that there is something can be seen at D1, and B is that for D2. Okay, sorry, A is that for hole 1 and B is that for hole 2. So, what will be the probability that there is. So, now you know all the possible ways things can happen, you represented it in terms of an amplitude. Now, you want to know, you can ask any questions out of that, like for example, I want to know that there is an event at something was detected at D1 and then there is an electron at X. So, how will I compute this event? You can just take this object A phi 1 B phi 2 and square it. Now, similarly, if I take down the B, which means there is no way the thing can come out to hole 2, which is equivalent to closing the hole 2. The B part is 0, then you get the A square phi square, which is the case of only one hole. And so, you can plot these objects and then you get a single peak, and when A is equal to B, you can show that you will get this interference pattern. So, this is basically the description of the act of observing the electron. Okay. Now, here comes a crucial conceptual point. So, let us say you want to know the probability that the electron arrives at X regardless of whether the photon was counted at D1 or D2. So, this can happen in two different ways. So, one is electron coming from S, photon coming from the light source, and then electron at X and photon is observed at D1, and the same phenomena where the photon is observed at D2. So, either way, in both of the ways it can happen, but you do not know which one happened. So, let us say you performed a measurement, but you did not look at that, it can, this is a possibility. So, when that happens, do you add the amplitude or do you add the probability? That is a good point which you should think about carefully. The answer is you should add the probability. Why is that? You did a measurement, but you did not look at it, then why did you that means you do not know what happened. Then why you are not adding the probabilities, why are you not adding the amplitudes, why are you adding the probabilities? So, this is one of the tricky situations which will help you to clarify the concepts. So, notice that this experiment actually has a different final condition, which means you are, in other words, even though you have performed if you have performed or disturb the system such that the system has different final conditions. So, this system has a different final condition from this system, because if I would have said that the electron at x, so that means there are two ways from that to happening, that electron came from S and reached at x. Okay. There are two ways it can happen, it can either go through hole 1 or hole 2, but here so their final state and end states are same, but there are two paths. When that is there, then you add the amplitudes, but in this case that is not the case. Here the final state of the system is different, because the final state includes what happens at the detector. So, in one case you saw a photon at D1, another case you saw a photon at D2. So, there are two different final conditions. When that is there, then you must add the probabilities, not the probability amplitudes. So, you must remember this. So, whenever you are in a state of confusion, think of this scenario. So, when the experiment is finished, the state of detectors have altered, the events have the things, the final event have happened, the final state has happened, even though if you have not looked at it, the final state of the system is different, and the state is everything together, which is the screen, the final screen and the detectors. But if you have not looked, then the final state of the system is just what happened at x and what happened at s, nothing in between. So, then you can add the amplitudes again. So, this tricky situation keep in mind, and that will it will be very useful. Okay, so that is all about the double slit experiment, and now the next thing we will do is Stern-Gerlach experiment, and that will be in a separate video.